For 38 years, one spacecraft carried a broken instrument through the most important boundary in the solar system and never knew what it actually crossed. Its twin did not have that problem, and when that twin finally reached the same boundary, what it recorded forced scientists to throw out the model they had been using for almost a decade. Everybody, this is the story of Voyager 2, and why the discovery it made in November 2018 is one of the most underrated moments in the entire history of space exploration. Not because it went somewhere new. Voyager 1 already went there first. This is bigger than that. This is about what happens when you send the exact same measurement twice through two different instruments, and the working one tells you the first one might have been misleading scientists for years. Let's go back to the beginning, because you need the full picture. Voyager 1 and Voyager 2 launched within weeks of each other in 1977, but they were never meant to follow identical paths. Voyager 2 actually launched first on August 20th, and Voyager 1 launched second on September 5th. But Voyager 1 was on a faster trajectory that let it overtake its twin before either one reached Jupiter. That single decision, which spacecraft took which route, ended up being one of the most consequential choices in the entire mission, and almost nobody talks about why. Voyager 1 was sent on the fast track, straight past Jupiter and Saturn, close enough to study Saturn's largest moon, Titan, in detail. That was its whole planetary tour. 2 planets, then out. Voyager 2 took what scientists call the scenic route. It visited Jupiter in 1979, Saturn in 1981, and then, because of an extraordinarily rare alignment of the outer planets that only happens once every 175 years, it kept going. It reached Uranus in 1986. It reached Neptune in 1989. To this day, Voyager 2 remains the only spacecraft in human history to have ever visited either of the ice giants. Nobody else has gone back. Nobody else has plans to. Everything we know about Uranus and Neptune up close, the geysers erupting on Neptune's moon Triton, the tilted magnetic fields, the storms, came from one spacecraft, one pass, decades ago. But that's not the discovery we're here for. That's just the resume. The real story starts after both spacecraft finished with the planets entirely and turned their instruments toward something far stranger, the edge of the sun's influence itself. Here's what you need to understand about that edge. The sun doesn't just light up the solar system, it inflates a massive bubble of charged particles around itself called the heliosphere. Think of it like a ship sailing through the ocean of interstellar space, pushing outward against the current. Eventually, far beyond Neptune, far beyond Pluto, that bubble runs out of pressure and the interstellar medium beyond it takes over. That boundary is called the heliopause. Crossing it means leaving the solar system's zone of influence entirely and becoming the first human-made object to sample the space between stars. In August 2012, Voyager 1 became the first spacecraft in history to make that crossing. It was a genuine milestone, and it made headlines everywhere. But here's the part that almost nobody outside the science community knew at the time. Scientists could not actually prove it happened for months. Not because the crossing wasn't real, because Voyager 1 could not directly measure the one thing that would have settled the question instantly. In 1980, decades earlier, during its flyby of Saturn, Voyager 1's plasma science instrument stopped working. This was the instrument specifically built to measure the density and speed of charged particles around the spacecraft, which is exactly the measurement you need to prove you've crossed from the sun's hot, thin plasma into the cold, dense plasma of interstellar space. When Voyager 1 actually crossed the heliopause 32 years later, that instrument had been dead for over 3 decades. Voyager 1 sailed through the single most important boundary of its entire mission, completely blind to the one number that would have proven it beyond doubt. So scientists had to improvise. They looked at indirect evidence instead. Cosmic rays from outside the solar system spiked. Particles from inside the heliosphere dropped off. Those were real signs, and they were enough to convince most of the team. But there was a second problem, layered on top of the first. Physicists had predicted that the magnetic field beyond the heliopause should point in a noticeably different direction than the field inside it. When Voyager 1 crossed, the field angle barely changed at all. One scientist on the mission, Stamatios Krimigas, summed up the confusion perfectly. He said nature apparently hadn't read the theorists' papers and didn't know it was supposed to change the magnetic field direction at the boundary. It was a discovery with 2 unresolved mysteries sitting right on top of it and no working plasma instrument to help settle either one. That is the exact problem Voyager 2 is about to solve, in a way Voyager 1 never could. Voyager 2 is heading toward its own heliopause crossing on a completely different trajectory, exiting through what scientists call the flank of the heliosphere rather than the nose where Voyager 1 broke through. And critically, 6 years after Voyager 1's crossing, Voyager 2's plasma science instrument was still alive, still working, still capable of doing the one job its twin's version could no longer do. If you're new here, this is exactly the kind of story we dig into. Real space history, real unresolved science, no filler. Hit subscribe so you don't miss the next one. On November 5th, 2018, Voyager 2 crossed the heliopause and became only the second human-made object to enter interstellar space. And this time, when it happened, the plasma science instrument was watching in real time. NASA later described this instrument's data as the single most compelling evidence of the crossing, because for the first time in the mission's history, scientists actually watched the plasma density jump the instant the spacecraft passed through the boundary, rather than reconstructing it after the fact. From secondhand clues. The readings show the electrical current detected by the instrument drop sharply to background levels across 3 separate directions, an unmistakable signature that Voyager 2 had left the solar wind behind entirely and entered the cold, dense plasma of interstellar space. This is what Voyager 1 physically could not do, not because scientists didn't want it to, because the hardware that could have done it had been dead since 1980. Within a year, 5 separate research papers were published based on Voyager 2's crossing, each one built around a different instrument on the spacecraft, the magnetometer, 2 particle detectors, and the plasma experiment itself. And when scientists compared what Voyager 2 recorded against what Voyager 1 had pieced together indirectly, some things lined up perfectly, and other things did not line up at all. Here's what matched. Voyager 2's magnetometer confirmed the strange result from Voyager 1. The magnetic field just beyond the heliopause really was roughly parallel to the field inside it, the same unexpected alignment that had puzzled the team back in 2012. With only one data point from Voyager 1, scientists couldn't be sure if that alignment was a real feature of the boundary or just a coincidence tied to where Voyager 1 happened to cross. Voyager 2 crossing in a completely different location and finding the same thing changed that. This wasn't a fluke. This was apparently how the boundary actually behaves, and it still isn't fully explained. Here's what didn't match. Voyager 1 had detected 2 brief pulses of interstellar particles leaking into the heliosphere just before its crossing, something scientists attributed to narrow tendrils of interstellar material poking into the bubble like roots pushing through rock. Voyager 2 saw something close to the opposite. Instead of interstellar particles leaking in, it detected solar particles continuing to leak out, trickling past the boundary and into interstellar space for some time after the official crossing. One planetary scientist studying the data called that difference very, very weird, and said it showed how much more data the team actually needed. 2 spacecraft crossing the same kind of boundary around the same star, and the boundary behaved differently each time. And this is the part that actually rewrote the model. Before either Voyager reached the edge, the leading prediction was that the heliopause would be a gradual, fuzzy transition. Plasma from the sun slowly fading out as interstellar plasma slowly faded in like mist thinning as you walk through it. Voyager 2's plasma instrument proved that wrong. The data showed a genuinely sharp boundary, not a blurred one, plasma density jumping abruptly rather than easing across a wide transition zone. Donald Gurnett, the lead scientist on Voyager's plasma wave instrument, put it directly. He said the data confirmed there really is a very, very sharp boundary out there. For a region of space scientists had modeled for decades as something soft and diffuse, discovering it behaves more like a wall was a genuine correction to how the entire scientific community pictured the edge of our own solar system. There was one more twist buried in the data that nobody had fully expected. Voyager 2's instruments picked up a trickle of low-energy solar particles that extended more than 100 million miles beyond the heliopause itself. Well past the boundary, scientists thought marked a clean cutoff. If the heliosphere were a sealed bubble, none of that should be leaking through at all. NASA's own description of the finding put it almost poetically. If the heliosphere is like a ship sailing through interstellar space, it appears the hull is somewhat leaky. A leaky hull on the only shield standing between our solar system and the raw radiation of interstellar space. That single detail is still being studied today because it raises a genuinely uncomfortable question. If particles from inside our bubble are seeping out through a boundary once thought to be a clean, sealed edge, what does that tell us? About how much protection that bubble is actually providing and how consistent that protection really is over time? None of this would have been resolved or even properly tested without Voyager 2's plasma instrument surviving long enough to do the one job its twin's equivalent hardware couldn't. Voyager 1 got there first, and that will always be true, and it will always matter. But Voyager 2 is the reason we actually understand what there is. It's the difference between witnessing an event and being able to prove exactly what happened during it. That plasma instrument didn't survive forever either. NASA made the decision to permanently power it down in 2024 to conserve the spacecraft's dwindling electricity. The same slow, forced shutdown both Voyagers have been undergoing for years as their plutonium power sources fade. Both spacecraft lose about 4 watts of power annually, and mission engineers have had to make increasingly difficult choices about which instruments stay lit and which go dark for good. The tool that finally resolved decades of uncertainty about the edge of our solar system operated for exactly long enough to do its job, and not much longer. NASA's team has said Voyager 2 should still have at least one working instrument into the 2030s, which means the mission isn't over, but the plasma chapter of this particular story is closed. So when you hear that Voyager 2 did something Voyager 1 never could, this is what that actually means. Not a new planet, not a new galaxy. Something quieter, and honestly, more important. It closed a scientific gap that had been open since 1980, using a piece of hardware that outlived its twin's equivalent by nearly 4 decades. And in doing so, it proved that the edge of our solar system isn't the soft, fading mist scientists had modeled for years. It's sharp. It's leaky in ways we still don't fully understand. And in at least one measurement, it doesn't behave the same way twice. 2 identical spacecraft, launched weeks apart, sent to the same kind of boundary from 2 different angles, using instruments with 2 very different fates. That's not just a footnote in space history. That's what real scientific proof looks like when you're lucky enough to get a second chance to gather it. Voyager 2 is still out there right now, still transmitting, still one of only 2 human-made objects to ever leave the protection of our sun's bubble. If this kind of deep, sourced space history is what you come here for, subscribe and turn on notifications, because these 2 spacecraft are still writing their story, and we're going to keep bringing you every chapter of it as it happens.